Hi guys, earlier on I promised that we're going to look at a second aspect of trying to describe the hydrogen-like species of atoms, whereby we first described how we can be able to show on how a radius of such an electron nuclear system is described. For today, we're going to look at the energy of an electron in a hydrogen-like species. And in this particular case, we're going to consider two aspects, which is basically the sum of potential energy and the kinetic energy of that particular system that we had mentioned. So therefore, in this particular case, I had looked at this system that I've said of a hydrogen-like species. And therefore, we had looked at some aspects of a circular motion, which created a basis for us in trying to describe the forces that were involved in this particular case. Earlier on, we had mentioned the concept of forces of attraction, the Coulombic forces that were experienced between the nucleus and the electron that is revolving around it. So therefore, that one gave us a basis of creating this particular relationship. So in a sense, we're going to use that specific formula from the earlier discussion in trying to describe how this particular system can be given in terms of energy. And therefore, as I've mentioned, this is the energy in this particular system is going to be the sum of the potential energy and the kinetic energy in this particular system. And therefore, we had looked at the concept of the principal quantum number that was giving the energy levels, and we had given it as the principal. This is the principal quantum number that we had given it an initial n. So therefore, for us to describe the energy at a particular level, which is n, is going to be the sum of the potential energy at that particular level and the kinetic energy that's going to be given as such. Now, for such a system, the potential energy of an electron basically is going to be the work that is going to be needed to get this electron as far away as possible from or remove this electron from this particular system. So therefore, this particular energy is going to be basically the Coulombic energy that we have described, which keeps this system in a stable state. Now that we said that this particular energy is equivalent to the centrifugal force, the centrifugal aspect that was, of course, being experienced by that particular system, that we of course describe as a centrifugal force that we had given as F, this small c. So basically, then we are going to look at this particular system by trying to describe those specific forces and the work that is necessary to remove this electron from this particular equilibrium position of R to infinity with respect to this specific nucleus. Therefore, we had mentioned that we can be able to represent these forces of attraction using this specific relationship, whereby we had this one given as 4 pi epsilon naught r squared as describing the forces of attraction that are being experienced between this proton and electron at this specific point. So therefore, the work that is going to be needed to remove this specific electron, which basically is going to be the energy, therefore can be described as the potential, the amount of potential energy at that specific point, which is going to be an integral of all the energies from that particular rate that is going to be required to remove that electron from that particular equilibrium position to infinity as such. So therefore, it's going to be the integral of these Coulombic forces that we had mentioned, which is Fa. And from this mathematical interpretation, therefore, we can just have a substitution for this and therefore have this potential energy given as the integral from R to infinity of this specific force, which is of course given as negative Ze squared over 4 pi epsilon naught squared r squared dr. So this is a relationship that is going to describe the potential energy, and this is going to give us, of course, negative Ze and then 4 as such. Now in this case we are going to include that particular sign, of course, which indicates the forces of attraction, and therefore for us to overcome this, it's the overall work that is going to be done to remove this particular electron, as we have said, from this specific point. Now that in a sense describes the aspect of potential energy of that particular electron insofar as the radius or the distance from the nucleus is concerned. Therefore, the second aspect that we have mentioned is, having described the potential energy, is the kinetic energy. And we're going to describe the kinetic energy from a classical point of view that we had said, which is a product of the square of mass and a product of mass and the square of velocity. And then we are going to have this one as half the product of mv squared. It's going to describe kinetic energy. Therefore, we can be able as well to describe the kinetic energy at a particular point, which is basically in this particular level for this particular quantum number m, which is going to be given as mv squared. Mv squared, that is half mv squared, given as such. Now, from this particular equation that we are given for n, this total energy at this specific point, this is for potential energy and this is for kinetic energy. Therefore, we can be able to describe the sum of this energy En by finding the sum of these two. So having seen that this is a force of attraction that keeps this system and it's a negative value, then therefore we're going to have En represented as this is mv squared over 2 minus ze squared over 4 pi, and this is epsilon naught r. Now if you try to look at this specific two formulae, earlier on we had described mv squared from a previous discussion, whereby we said that we can be able to represent this aspect from the Bose relationship. We can be able to represent mv squared, whereby we had said that mv squared is equivalent to ze squared over 4 pi, and this was given as that. So therefore we are going to see that if you try to compare this one with the kinetic energy that we have described in this case, so this is going to be a division, because there's a comparison that I'm trying to. Therefore, if you try to look at this, the mv squared over 2 is equivalent to this particular value, and therefore half of this, which is mv squared over 2, will be equivalent to, of course, ze squared over 2 4 pi epsilon naught r. So therefore this is going to transform this particular value to 8. So and that is going to be that specific relationship. So therefore we can be able to illustrate this specific formula of that difference, whereby we're going to have En being represented as half mv squared, which is this particular section, and now which we're going to substitute using that particular figure. So it's ze squared over 8 pi epsilon r, and then minus this particular value, which is ze squared over 4 pi epsilon r. So basically this is implying half minus this specific quantity. If we try to do from basic mathematics, then therefore we're going to have a negative half of this value, which is going to remain. So therefore we're going to have this one given as negative ze squared over 8 pi epsilon r, given as that. And this is going to imply the En value that we're going to describe. But we had mentioned earlier and said that from the first discussion, the R represents the Bose radius from this hydrogen-like species. So therefore, having seen that this is going to represent En, we can be able to bring in the concept of a Bose radius from this particular case. and we are given it as r equivalent to n squared h squared, and then this was all over pi m z e, and this was, there was an epsilon at that particular point, and this is a square of that specific charge. So that was a formula that gave us what we refer to as Bohr's radius. So therefore, considering that this specific r can be substituted for Bohr's radius, therefore we can be able to have this particular energy represented, which is En, represented as a substitution for this r in this specific formula. Therefore, this is going to give us a general formula for negative me to the power 4, and then this is going to be z squared over, this is n squared h squared. This basically are constants, so therefore we are just going to look at the value of this particular energy as a substitution of those various constants, and try to see which basically in terms of a value, what is it going to be that equilibrium position of r. So if we try to do a substitution for those various constants that you have already mentioned, we're going to see that the value of En, where n, as we have said, is that specific a level, and therefore it's going to give us negative 2.122, and then that is 10 negative 18 joules. This is negative 18 joules. I hope it's legible from that specific point. And then this is going to be over the ratio between this value and the square of that particular orbit, which is n. So for a hydrogen-like atom, we say that the value of n is equivalent to 1. So therefore, if you try to do a substitution for this, then therefore we're going to see that the energy of an electron in this specific electron nucleus model for a hydrogen-like atom is going to be having the value of 2.122 times 10 negative 18 joules. And if in this particular case we had decided that this negative value basically try to give that aspect of attraction that we had given from this specific relationship at that particular point. So therefore, given this particular information, therefore we're just going to use the same procedure in trying to describe this aspect of energy of an electron in a hydrogen, or a hydrogen species. But of course, we're going to see that in us trying to represent this, we're going to have these different energies for different other atoms. So therefore, for this specific kind of a model, then therefore, that is the only solution that we can be able to use in describing its energy. So having looked at the first case for describing the distance and then the energy at this specific point, therefore it will be relevant for us in trying to look at other aspects like the spectral lines of this specific model, and some of the ways in which have been forwarded in trying to describe these different spectral lines and their characteristic. So in a sense, I'd like to invite us into our next video, which is going to look at these spectral lines of such a kind of a model, which is going to assist us, of course, in trying to figure out how other spectral lines can be described. So that is it for now, guys. Bye. Welcome to another video, and check on our description box for other videos related to this. Like and subscribe to our channel for more updates. Thank you.